class started. All right. So, since we are done with two's complement and signed versus unsigned representation, we are starting on binary comparison today because I'm just moving down in terms of the topics. So that means you can always read ahead of time because from your perspective, a lot of these things is not appearing on your side because they're either obsolete or we're not quite ready to deal with those yet. The lab that we are doing is today's lab is about subtraction and compare, which is basically using the stuff that we will be talking about in this module. If you have read a little bit ahead of time, that would make it easier because you're already somewhat familiar with what we'll be talking about. Maybe still have some questions about the details, but at least you have a general sense of what the topic is and why it is important. So we'll go ahead and start with this module. And the first thing is, we only need to know whether something is less than something else, okay? Because if you want to know whether something is greater than, you just have to switch the two sides, okay? So let me just kind of quickly explain why only less than is important. So let me switch back to my tablet, which is here. So if you know how to do this, okay, if you can confirm one way or another whether x is less than y, then the other one is easy, okay? Because if you need to determine whether x is greater than y, that is just, whether y is less than x, okay? So that means just by exchanging the two sides, you can now, deal with greater than. What about x is less than or equal to y? Well, this is the same thing as not y is less than x. Okay. Well, okay. Does it make sense? If x is less than or equal to y, then y is not less than x. Does that make sense? Okay. All right. So now we have the other one, which is y x is greater than or equal to y. Well, okay, fine. We just have to change the ordering. Okay. Now we can deal with it. So now we have x does not equal to y. X does not equal to y means x is less than y or y is less than x. And then finally, we have x equals to y, which is the negation of the one above. Okay, so we can just say a whole big negation of x is less than y or y is less than x. So from this translation, you can see everything on the right-hand side. They only involve logical operators or less than. So that means, as long as I can compare two values and I can tell whether the first is less than the second, I'll be fine. Okay, so do we have any questions about that statement? I can get away with only implementing one single comparison operator. The rest can be implemented using just less than. So we good? Yes, go ahead. Why would we do that? Okay, so this is a great question. Okay, the question is why do we want to kind of lean in this direction? If there's one way to do it, and the rest can be emulated using that method, then we'll just kind of use the simplest method. That's the general idea behind RISC, RISC, which is Reduced Instruction Set Computer. In other words, you're trying to minimize the number of instructions, so instead of having one instruction to check for less than, one instruction to check for greater than, one instruction to check for less than or equal to, and so on, I just need one. Right. So I would use logic, which is going to use and make the program a little bit longer in order to make the silicon smaller. So that's the general philosophy of RISC, which is you try to optimize the hardware, so you're using less transistors and not as much silicon, and then you use more multiple instructions to do the same thing as what one single Cisp instruction would do. Yes. Hmm? So it depends on what is the bottleneck of how much processing power you can fit into a data center. And right now, if I understand correctly, it is heat dissipation. In other words, the wattage of your processor. So as it turns out, Cisp processors, in order to get the same amount of computation done, they need more energy, despite each instruction can do more. But because you have a lot of basically deadbeat transistors that are not really doing anything at any particular time, so they are actually less efficient from the energy perspective. So most data centers would use RISC processors or specialized processors, like for neural network type of computation, they have specialized processors for those. All right, that's a good question. Any other questions about what I have shown on the projector at this point? Okay, assuming there are no questions, we are then moving back to the notes here. So now the question is, what is the interpreted value given a particular bit pattern? I was trying to illustrate to my class last semester, which part has to do with definitions, and they are super important. So those are the ones in the green rectangles. Okay, but I want to explain too. Okay, so assuming that you have m bits, okay, to represent values, VU, is representing the unsigned interpretation of a bit pattern. Okay, what is the value interpreted as unsigned, given that you have a bit pattern called X and you're using up to M bits? Okay, and then some of you will say, but Tech, we talked about this last Thursday. Yes, we did. So that means, this is nothing new. Okay, this is something that we have already talked about. So VS, on the other hand, at the bottom here, that is for signed interpretation. I give you the same bit pattern, but this time I'm trying to interpret the bit pattern X as a signed value and up to M bits. And you can see that this almost is exactly the same as this. Now, this one, okay, for unsigned value, it is basically a special case of base conversion. That formula or that sigma notation was first introduced in base conversion. Okay, in this case, it's a special case, which means, oh, we know the base already. It is base 2. Okay, what about the digits? Well, we only, because these are signed and unsigned integers, so we don't have fractions to deal with. So that means we start with digit 0, and that's why index I, or the index variable I, starts with 0 and then it goes all the way up to only m minus 1, because that would give me exactly m digits. Are there any questions about this? Yep. No, it has nothing to do with one's complement. All right, so given these definitions, let's go ahead and try a few examples. And I want you guys to give me, let's say, a 6-bit representation. Okay, just give me a string of 6 bits, and then we'll try to look at it from the signed perspective and the unsigned perspective. 1 0 0. Okay. All right. So this is a base 2 number. It has 6 bits. So the VU, and we'll call this X, being the bit pattern. And since it has 6 bits, we'll just interpret up to 6 bits. Now, you can always make the number of bits to be less than the actual number of bits that are given to you, which means you're only doing a partial interpretation of the bit pattern. But we are interpreting all 6 given bits in this case. So what would that be? Well, the sigma notation says, we have 0 of 1, we have 1 of 2, we have 1 of 4, we have 0 of 8, we have 0 of 16, and then we have 1 of 32. So now you just have to add all of these up. We got 1 plus 2 plus 32, and that would be 35 in base 10. Okay, so I just did the base conversion. Okay, because VU is the base conversion sigma notation. Yes. 2 plus 4. Yep, you're right. Copied it wrong. Thank you. To get rid of that. Thank you, thank you. 2 plus 4, so that means it's going to be what? 38. Okay. Yep. Well, 35 would be kind of stupid as an answer because any odd number would have a 1 as bit 0. So, so thank you for the correction. Um, but generally speaking, do we have any questions of how to apply VU to interpret the unsigned value given a particular bit pattern? We good here? All right. So now we are going to look into VS. Okay, same thing, the signed interpretation of this. So it's almost exactly the same thing. It's 0 times 1, 1 plus 1 times 2, 1 times 4, 0 times 8, 0 times 16, and then we have a 1 times 32, except that is subtracted. Okay, so now we have 6 minus 32, which is negative 26. So do we have any questions about how this example illustrates the application of VU and VS as functions? Yes, exactly. So right now, we're having pretty much just a warm up, to the actual topic. So are we good so far? All right. So now we want to think about, okay, so what does this have anything to do with comparison? So remember what we kind of talked about last time, your adder and subtractor, discussion, it will work regardless of whether you're working with signed or unsigned values. Okay, I already demonstrated that in the previous class. So the idea is this. Okay, let's look at some subtractions here. So this time I'm going to switch back to only 4 bits, just because it's easier to deal with it. So now we will look into 0, 0, 0, 0, minus 0, 0, 0, 1. This is x, this is y, this is q, t, d. Okay, so this is a 1, 0, 0, 0. This is a 0 to assume because we don't have a prior subtraction to deal with. And then these would be 1, 1, 1, and 1. And then this would be 1, 1, 1, and 1 here. Okay. So the way I worked out all of these bits is based on binary operation. It's based on how the Q is defined using the X and Y, how the T is defined using X, Y, Q, T of the previous column or the column to its right hand side, and then D depends on Q and T only. Okay. So if at this point you don't know the relationship between the digits, I would say you have some studying to do. Okay. At least you should know where to find how each digit is computed by the other digits. You are given with only x, y, and t0. Everything else can be computed using logic gates. All right. So I'm just telling people where they're supposed to be at in terms of the understanding of the material. Okay, so this is one. We'll work with another one. So we'll work with 0, 0, 0, 0, minus 1, 1, 1, 1. Okay, so once again, we have x, y, q, t, and then d. This would be 1, 1, 1, 1. This is a 0 by default. We have 1, 1, 1, 1 here. And then finally, we have a 1 here, and then 0, 0, 0 here. Are we doing okay so far with this? All right. So when we look at this, we are going like, but what is the importance of this? Well, as it turns out, we're trying to decide if I want to know whether x is less than y, okay, what is a clue? Okay, what can tell me about whether x is less than y? So the first thing is, we'll go ahead and try to look at things from the unsigned perspective first, okay, because that's actually easier one. So what do you think is an indicator of whether x is less than y? If I need to look at one single bit that is part of the calculation, which single bit will tell me whether x is less than y, but only from the unsigned perspective? Yes, yes. So the most significant t digit, which will be t4 in this case, is going to tell me whether x is less than y. T4 is going to be a 1 if and only if VU x4 is less than VU by 4. Okay, so let me go back to the notes. Okay, and this is also why it is important to read the notes first, because that's exactly what the note said. Okay, which is right here. Okay, in a binary subtraction of two m-bit patterns, x1, xy, x minus y, t of m equals to 1 if and only if VUXM is less than VUYM, assuming t0 is a 0. Okay, so now there are a few questions, right? One is, do we understand the notation, what it is trying to state? And the second one is, are we sure? How do we know this? Okay, so the proof of how this works, which is proof by induction, is right below, here. Okay, so there's actually a proof, for the entire thing. You don't have to understand the proof, not in this class, okay, because this is not CISP 440. I do not teach the technique of proof by induction. But if you have taken CISP 440, you might want to kind of look into the proof itself and see if you can understand, the proof itself. If you're going to take CISP 440, you can remind yourself, oh, okay, when we get to proof by induction, there might be a proof I can revisit just to see whether I have an understanding of that proof at this point or not. Yes. No, T0 may not be zero when you have a multi when your subtractor is too narrow and the actual integer that you want to subtract is wider, then you chop it. That is when that's when your T4 from one subtraction becomes the T0 of the next subtraction. You hmm? It bumps over basically, yes. Because the T4 of a previous of the less significant digit subtraction becomes the T0 of the next chunk of bits that you want to subtract. So that's how you can have a 4-bit subtractor, and you can still deal with 8-bit numbers, 16-bit numbers, 32-bit numbers, and so on. You basically stack it in a direction, a certain direction. So we're not going to get into that, because we want to focus on comparison right now. But maybe at some point we'll talk about why T0 is so important because it's an input pin. All right. So that means, because the proof is not important in this class, so that means the green stuff, okay, the stuff that is inside the green rectangle is the only part that is important. But do we understand what that is saying? Do we understand what it means when I say Tm equals to 1 if and only if VUXM is less than VUYM? So there's a whole lot of notation. The only way to understand the notation is to read the module. Okay, so without reading the module, coming to the class code may not be the best strategy. Okay, because then it and also taking notes is important because the whole idea of VU and VS was already introduced in the class, last Thursday's class. Okay, so there's not a whole lot of stuff that is new here. All right. So given that is the case, okay, and we can go back to our example to kind of find out whether that really is the case or not. So the first one is, x, if we look at the unsigned value, x is 0 and y is 1. and the borrow bit T4 in this case is a 1. So 0 is less than 1 is true. Okay, cool. In this case, x is a 0, y is 15, and 0 is less than 15 is also true. And you look at the T4, it is also a 1. So everything seems to be consistent. So now we look at, what about when x is not less than y? So we look at the boundary case first, which is when they are the same. So we have 1, 0, 1, 0 minus 1, 0, 1, 0. Now this one is not very exciting. I think all of you know the answer already, but we're going to go through that anyway. Okay, this is x, this is y, this is q, t, and d. So that's a 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, very exciting there. Okay, but hmm, it's 10 minus 10 from the unsigned perspective, right? So we have 10 minus 10, and then we say 10 is less than 10 is false. Ah, okay. So T4 does correctly indicate that, 10 is not less than 10. Okay, cool. And then we're going to look at yet another case. So we're going to look at a case where we have, let's say 1, 0, 0, 1, and that's my x. And then we subtract, say 1 from it. Okay, 0, 0, 0, 1, which is y. Okay, this one is also super easy because there's no borrow of 1 in this case. So that's a 0, 0, 0, 1. And then we have 0 assumed, 0, 0, 0, 0. And this is just going to be 1, 0, 0, 0. So in this case, x is representing 9 as an unsigned value, y is representing 1 as an unsigned value, and we are asking, is 9 less than 1? The answer is false, and the T4 is correctly indicating that x is not less than y in this case. So are we still doing okay so far? Okay. So if you need to tell whether x is less than y in a binary subtraction, all you need to look is the most significant borrow bit or the t bit. Is that okay? All right. So unsigned is easy peasy. Signed, on the other hand, is a little bit trickier. Okay, even though it is not supposed to be. All right. So we look at the general case of x is an integer, y is an integer. How do we know x is less than y? Well, let's see what happens when we subtract y from both sides. Okay, so if you subtract y from both sides, then just using algebra, then we have something like this, right? But x minus y is also called the difference. So that means if the difference is less than 0, then we know x is less than y, given that x and y are both integers. X can be positive or negative, y can be positive or negative. They're signed integers. Is that okay? So now the question is, how do we know whether the difference is negative or not? So the whole thing goes back to the VS notation. So let me go back to the module itself and just scroll up a little bit here. Okay, this is how VS is defined. So the first question is, the only thing that can make the quantity, the entire thing, to go negative is what? Where is the only subtraction? So yeah, so the most significant bit, which is x subscript m minus 1 times the power of 2 corresponding to that digit, which is 2 to the power of m minus 1, is the only quantity that we are subtracting from the rest. So now the question is, can the sigma notation ever add up to the point that is greater than 2 to the power of m minus 1? Okay, so we think about this a little bit. Okay, what if m equals to 2? Okay, then we are looking at 1 which is the entire sigma, and then minus 2, which is the most significant bit, okay, that's negative. And then you look at the next one up, okay, let's assume that m is 3. If m is 3, then this sigma is going to go from 0 to 1, which means it is 1 plus 2, which has a sum of 3. 2 to the power of 3 minus 1 is 2 to the power of 2, which is 4. So that means, okay, so from this observation, the sigma, if you look at the absolute value of the sigma notation, it can never be more than um, 2 to the power of m minus 1. That's an observation. It is not a proof. So there's a way to prove that as well. Okay, it is also, you can prove by induction as well. So proof by induction is one of the most useful proof technique in computer science. Okay, but I'll just go ahead and make a general statement here to basically say no matter what the other bits are, okay, the maximum of your sigma notation can never make up for 2 to the power of m minus 1, which means if the most significant bit is a 1, then the value, the signed value that is being represented is going to be negative. Very good. Okay. And that is also why the most significant bit is also known as the sign bit. Okay. If the sign bit or the most significant bit is a 1, then the signed value being represented is guaranteed to be negative. Is that concept okay? All right. So given that is the case, okay, so now we go back to the tablet and we go like, oh, okay, so this happens if and only if d subscript m minus 1 is a 1. Now, how far negative is d? I don't care, okay? As long as it is negative, we know that x is less than y. Are we good? Are we doing okay so far with the math? Okay. Well, that's not too hard. Okay, so we'll go back to the previous examples and take a look. So now I switch back to the previous page. The first one, your sign interpretation, 0 minus 1 is -1. And this time we look at the sign bit here. Okay, this is telling us that 0 is less than 1 is true, even with the signed interpretation. Well, if the most significant bit is a 0, then it doesn't really make a difference whether it is a signed versus an unsigned interpretation. So we look at the next one. In signed interpretation, this is representing 0, or x is representing 0. What about y? What is y representing in signed interpretation? It is 1 plus 2 plus 4, and then what did we do with the 8? Yes, it is -1 as a total, exactly. So 1111 as a 4-bit pattern is representing -1. 0 is less than -1 is false. Ah, okay, it's good because the sign bit of the difference is also a 0, meaning the difference is not negative. If the difference is not negative, then x is not less than y. Everything seems to be consistent. Are we still doing okay so far? Okay. And then we look at the next one. Okay, even though that one is a little bit stupid, but we'll take a look too. So now let me move the clock here. So we now look at the top one, okay, in the sign interpretation. 1010 is 2 minus 8, which is -6, okay? But, -6 minus -6 is a 0. I don't even care whether it's a 0 or not. All I need to know is this bit here. So now I can say -6 is less than -6 is false. So far, so good, right? Seems like the sign bit is very reliable to tell us whether the sign interpretation of the bit patterns, whether x in sign interpretation, whether x is less than y. So far is very consistent. And we'll take a look at the last one. So 1001 is representing the value of 1 minus 8, which is negative 7. Okay, so we have negative 7 here. 0, 0, 0, 1 is just 1. So now we are saying negative 7 is less than 1 is true because that's what the sign bit of the difference is telling us. That is also consistent. Okay, negative 7 is indeed less than 1, and the sign bit is telling me exactly that. Yes, so far, yes. Okay, and then I'm going to throw a wrench into this whole thing and go like, it doesn't work. Okay, so now we look at a few more examples where it does not work anymore. Okay, so the way it doesn't work is easy. Okay, we have 1, 0, 0, 1, and then we're going to subtract 0, 1, 0, 0 from it. Okay, x, y, q, t, k, oh, d, and this is a 1, that's a 0, that's a 1, that's a 1, that's a 0 assumed, there's a 0 here, that's a 0 here, that's a 1 here, and that's also a 0 here, and then we have 1, 0, 1, 0 here. Okay, all right. So we're going to take a look at both the signed and also the unsigned interpretation. So using the signed unsigned interpretation, that's the easier one. We'll look at the unsigned interpretation first. This is a 9, this is a 4, and then we are saying 9 is less than 4 is false. Okay, so the T4 is still okay. Okay, in the unsigned interpretation, we don't have a problem. Now we look at the signed interpretation. So using the signed interpretation, 1 minus 8 is negative 7. 0, 1, 0, 0 is a 4. And according to this, 7, negative 7 is less than 4 is false based on the sign bit of the difference. You guys go like, what? Negative 7 is less than 4. Why do we think that it is not? Hmm. So this is one scenario where it's not working anymore. Is that okay? Does everybody understand what this example is trying to illustrate? The sign bit of the difference is now not consistently telling us whether x is less than y. Okay, so there's another example, for something like this. Okay, so we'll take a look at the other example, and I have to think about it a little bit. Okay, let me flip to a new page. So we have 0, 1, 0, 0, 1. Okay, and we'll subtract 1, 1, 0, 0 from it. Okay, so 0, 1, 0, 1. There's a 0 here, 0 here, 0 here, 0 here, and a 1 here, and then 0, 1, 0, 1. There we go. All right. So once again, we have signed versus unsigned versus signed interpretation. Unsigned, this is a 6. This is a 12. 6 is less than 12 is true. The borrow bit is telling us the truthful answer. It's all good. In the signed interpretation, 6 is still 6. Okay, 0, 1, and 0 is still a 6. 1, 1, 0, 0 is 4 minus 8, which is negative 4. So we say 6 is less than negative 4 is, this bit is telling us the answer, which is true. Okay, and you guys are now going like, what the? It's wrong. 6 is not less than negative 4. So the sign bit of the difference, again, has betrayed us. Are we good so far? So now the question is, why is the sign bit of the difference not telling us the correct answer? Yes, go ahead. Because we're only using 4 bits. And if you look at the actual value being represented, what is 0010? In other words, if I look at this bit pattern here and the actual difference in sign interpretation, what is it? It's, come on. What it's 1010. Thank you. So 1010 is representing what value as a signed interpretation? Is -6. Yes, it is -6. Um, but it doesn't make sense because in signed interpretation, 6 minus -4 should have been, what is 6 minus -4? 10. But it's giving us -6. In other words, in the sign interpretation, VS 10104 is -6. You go like, but that's not the right answer, okay? Because it was 6 minus -4 should have been a 10. Why do you think we have a problem here? Yep. Nope. Has nothing to do with T4. T4 is fine. All right. So let's go to a new page here. And this time we'll look at the range of value that can be represented. Okay. In other words, we're looking at min and max here. And we have signed and then we have unsigned. And we are using M bits. Okay. Yes. That is correct. Okay, but we can also look at it from the perspective of VS versus VU. Okay, so we'll start with unsigned first. Okay, in other words, here we'll answer this question first, and then we'll go back and to answer this and this. Okay, so let's go. Let me use a mouse pointer to kind of point here. So given that we have M bits to play with, what is the minimum value that can be represented? Hmm? No, minimum. No, it's just zero. Every bit is a zero, then you are multiplying zero to all the powers of two, which add up to just zero. That's the least amount that we can have. Does that make sense? Okay, so we just go like, oh, okay, that's an easy one. What about the maximum? In other words, every single bit is a one. Okay, so we're adding 1, 2, 4, 8, all the way up to 2 to the power of m minus 1. So what is the value of adding powers of 2, okay, from 2 to the power of 0 all the way up to and including 2 to the power of m minus 1? It would be, you can look it up, okay? The answer is in the module. You can look it up. Yep, it's 2 to the power of m, the whole thing, minus 1. It is in the module, okay? So reading ahead of time, once again, is really kind of important. So you go like, okay, so once I have introduced these values, especially the maximum of an unsigned m-bit integer, and I conclude that it is 2 to the power of m minus 1, what are you thinking? Okay, I shall memorize this. Okay, okay, it's not a bad idea. Two, how do I know this? Okay, can I plug in some values and just see how this works? Let's say m equals to 4. Okay, if m equals to 4, what is the maximum? No, for unsigned, we are still talking about unsigned. 2 to the power of 4 is 16. 16 minus 1 is 15, right? So now you flip back into your earlier pages in your notes, okay, about the number wheel. What was the largest number or largest value on that number wheel? 15. Okay. So at least it is consistent. Okay. So if you want to push yourself a little bit more, then you ask, why is that the case? Can we prove that given m bits, The largest unsigned represent the largest unsigned value it can represent is 2 to the power of m, that whole thing, minus 1. So those are the questions that might go through your mind, okay? Knowing just this part here is useful. It means, if you are given, oops, that means if you are given a 32-bit number, you know what is the largest value the 32-bit number can represent. Okay, now why is that important? Integers are integers. Why do I care? Is that practical? I mean, do I really need to know? Go ahead. Okay, so you can, knowing the range of values that can be represented by a certain width of integer means that if you know the range of value that your program needs to handle, and that is exceeding what you can represent using 32 bits, then you go like, oh, I need to use a larger or wider integer, like a 64-bit integer. Does that make sense? Now, most people would look at a 32-bit integer and go like, but that can go to like 4 billion something. I mean, that's a large number. I would never run out. Or okay, that it doesn't make sense in this case, but I was about to say uh, the um, the deficit of the United States. Yeah. hmm Um, but it is important, okay? Because I cannot tell you how many times. Let's say you have a program, okay, and you are emulating motion control and some other really cool stuff on the PC, okay, and you're using GCC, using GDB, everything works fine, okay. So you port that code onto an Arduino, platform, okay, and then suddenly things only work up to a certain point, and then the program blew up. Why? The logic is still the same. It is a slower processor, but it still should not blow up. Yes. Hmm? Nope. Nope. If it's out of RAM, the compiler would have complained. Yes. Okay. And I'll collect all the answer and then I'll kind of comment. Go ahead. Okay. Go ahead. Uh-huh. Okay. And okay. So the concept is, the compiler, when you say int or unsigned, okay, the number of bits or the width of the unsigned depends on the compiler. Okay. When you are using a native compiler on a 32-bit platform, it is most likely that an unsigned is also 32-bit wide. If you're on a 64-bit platform, it is very likely that an unsigned is also 64-bit wide. The Arduino processor is only 8-bit, okay, it's an 8-bit processor, but unsigned is actually 16-bit wide. In other words, unless you do something on your part, you really don't know how wide a unsigned is, and therefore you do not know for sure what is the range of values that it can represent. So when you're writing a program on a PC using regular GCC, or basically VS Code has GCC as a backend anyway, you're dealing with 64-bit unsigned integers. So that means the largest value that can be represented is 2 to the power of 64 minus 1. That's a huge value, okay? But when you port that program, meaning you just copy and paste the program and make it compile inside Arduino, an unsigned integer is only 16-bit wide. It's only 16-bit, which means the largest value is only 65,535. That's considerably less than 2 to the power of 64 minus 1. And that can lead to issues. So later on in this class, I will introduce a header file called stdint.h, which is standard integer.h, where you can use specific type names. So even on an Arduino, you can say, I want to use an uint64 underscore t, which means I want a 64-bit unsigned integer. you can still use that type. Okay, it will take a little bit longer for the Arduino to do all the additions and subtractions and whatnot, but your program at least will still work. Okay, so that's why knowing the width of your integers is actually very important. Okay, depending on what kind of calculation you're conducting in your program, this can be very important. Okay, so now we get to something. Yes, it will allocate enough bytes to cover 64 bits, which is 8 bytes, right? And it's usually consecutive. There's no reason why it should not be contiguous, and but it will generate the correct code to deal with it. All right. So now we are moving from unsigned, which is easy, to signed. So now can someone tell me with only m bits, what is the smallest value you can represent? Okay. So think about the VS notation. You have a sigma of a bunch of bits minus the most significant bit times 2 to the power of m minus 1. Okay, so how do you make the least value out of all the digits? It's a very simple math problem. On one side, you have 1 times, put whatever bit times 1 plus whatever bit times 2 plus whatever bit times 4, and so on. And then suddenly you have a minus whatever bit times 2 to the power of m minus 1. So how do you make the most negative value of the entire thing? Go ahead. Well, okay, so we are talking about arithmetic here, okay? I want this entire quantity to be as negative as possible. How can I make that happen? Make this a 1, make all of those zeros. Does that make sense? Okay? And if that is the case, what is the value being represented? It would be, well, okay, negative, no, not -7. It will be, this entire thing is going to be a 0 because those are the terms that can contribute to make it not as negative, right? We want to make this as small as possible. So all of these bits are zeros. This bit has to be a 1 because that's the only contributor to make it negative, right? So if everything here are zeros and this particular bit is a 1, then this is the most negative value. It's 2 to the power of m minus 1. The exponent is m minus 1. Does that make sense? Okay, very good. So yes, so you can memorize the things that we talk about in this class, but being able to look at how a signed value is represented and come to and logically deduce that this is the value is even more important. Is that okay? All right. So I'm just trying to focus on not only what you need to know, but also how you can reason out the whole thing and come to that conclusion yourself. All right. Okay. So now what about the maximum? Okay, so we look at this quantity again, and this time I'm saying, okay, how can I make this entire term as positive as possible, the largest positive value? Exactly, okay? We need to make this one a 0 because we don't want the whole thing to go negative, and then we'll make every single one of these a 1. So that means we're adding 1, 2, 4, 8, all the way up to 2 to the power of m minus 2, and the sum of all of those is 2 to the power of the exponent of m minus 2, excuse me, m minus 1, and then that whole thing minus 1. Okay, so we go back to the tablet, and then we come to the conclusion that this is 2 to the power of m minus 1, and then that whole thing minus 1. But is that consistent with your number wheel? on the number wheel of 4 bits, what was the most negative value on that wheel? -8. So given that there are 4 bits, is -8 the same thing as 2 to the power of -2 to the power of m minus 1? Yep. What about the most positive value when you look at the number wheel from the signed perspective? It was nope, 7. Because -8 and 8 would occupy the same spot, which is 1, 0, 0, 0. But based on the interpretation VS, okay, that particular bit pattern is -8 and not 8. So that means the most positive value is just 7. 7 also is 2 to the power of 4 minus 1, which is 2 to the power of 3, which is 8, and then the whole thing minus 1. So that works out as well. Is that okay? So I'm trying to look at the same thing from many different perspectives. Okay, we look at it from the number wheel perspective. We look at it from the equation perspective. We look at it from just arithmetic from the arithmetic perspective. So that's kind of how I teach this class and most of my other classes is to look at the same thing but from multiple perspectives. Are we still doing okay so far? Okay, all right. So now that we understand this part here, we go back here. Are we getting our answer? What is the value of 6 minus -4 outside of the context of binary subtraction? If you are simply asked what is 6 minus -4, it is 10. And is 10 within the range of values that we can represent using only 4 bits as a signed value? That's it. Okay, so whenever the difference is outside of the range of the values that we can represent, then the sign bit lies. The sign bit will tell you exactly the opposite of what it should be when it is outside of the range, which is known as overflow. Okay, so let me say that one more time. Overflow is when a signed subtraction has a result that is outside of the range of what the signed interpretation can represent. You don't have to write it in exactly those words. I think you guys get the general idea. Okay, okay, so that's kind of makes sense. Okay, so how do we know that we have an overflow situation? In other words, I have demonstrated two overflow situations here. This is also an overflow situation because what is -7 minus 4? -11. Is -11 outside of the range of a signed 4-bit integer? Yes. And as a result, oh, look at this sign bit here. It is not what it is supposed to be because it is out of range. So what do you notice? Yes, go ahead. Because we know from normal math that -7 minus 4 is -11. That's how we know what it is supposed to be. But, yes, go ahead. That's it. That's what we are trying to figure out, right? So the way we figure that out is we look at the sign bits of x, y, and the difference. Okay. So we'll look at a few, normal cases, which is, the page before, and then we say, okay, does the sign bit of the difference make sense? Okay, we'll look at one case at a time. Okay, we look at the first case here. X is non-negative, y is non-negative, and the difference is negative. Can that happen? You are subtracting a non-negative value from another non-negative value, and the difference turns out to be negative. Can it happen? Okay. So if it can happen, we go like, okay, fine, no overflow in this case. Okay, we look at the next case. So the next case is this one. You are subtracting a negative quantity from a non-negative quantity, and the result is non-negative. Does that make sense? Okay, so no overflow. Just from the signedness of the difference with respect to the x and the y. And then we look at this one over here. You are subtracting a negative quantity from a non-negative, from also a negative quantity, excuse me. So you're subtracting a negative quantity from a negative quantity, and the difference turns out to be non-negative. Can that happen? Okay, so no overflow either. Okay, so no overflow. And then finally, we look at this one here, which is you start with a negative quantity and then you subtract a non-negative quantity from the negative quantity, and the result is negative. Can it happen? Okay, so no overflow. Then we look at the two cases where we do have an overflow. So you start with a negative quantity, you subtract a non-negative quantity from it, and then the result is non-negative. Does that make sense? So we do have an overflow here. And then the last one is this one here. You start with a non-negative quantity and you subtract a negative quantity from the non-negative quantity, and the result is negative. Does that make sense? Okay, so this one also has an overflow situation. Okay, so are you convinced at this point that if I just look at the sign of x, the sign of y, and the sign of the difference, I can tell whether there's an overflow or not? Okay, yes, go ahead. Exactly. Yep, yep. So we'll get to that. Okay, we'll get to that. So now we make a truth table. Okay, x of m minus 1, which is the sign bit of m, y m of y m minus 1, which is the sign bit of y, and d m minus d of m minus 1, which is the sign bit of the difference. Three independent variables, so there are 8 rows, because you can have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Oh, okay, there we go. And now I ask you, do we have an overflow on that particular row? In other words, this is just a summary of kind of what we did. You are subtracting a non-negative quantity from a non-negative quantity, and the result is non-negative. Can that happen? If it can happen, it is not an overflow. If you are subtracting a non-negative quantity from a non-negative quantity, but the result is negative, can that happen? It can happen. So that means it's not overflow. If you subtract a negative quantity from a non-negative quantity and the result is non-negative, can that happen? Not only can it happen, it should happen, right? Okay, so it's not overflow. If you subtract a negative quantity from a non-negative quantity and the result is negative, can that happen? If it cannot happen, it is an overflow. And then, I will just kind of quickly fill out the rest of the table, okay, because it gets boring. You are subtracting a non-negative quantity from a negative quantity and the result is non-negative. Can it happen? For those people who said yes, name one. It cannot happen, okay? You're starting with, yep, because you are moving more on the negative side. So this cannot happen is a one. The rest are zeros, okay? I'm not going to bore you guys with all of the other stuff. So that means we have two scenarios where there's an overflow. So if I need to make a Boolean expression to express overflow, what do you think that's going to look like? So overflow is going to be what? Well, we'll focus on one row at a time. How can I make this row to return a zero? What kind of expression will make only this row, the fourth row from the top, to return a zero? Well, I mean, what about this? We negate x m minus 1, and then we do a conjunction. Okay, I'm going to use conjunction here and then conjunction here. Okay, so if you look at this entire conjunction, this kind of big conjunction here, don't you think this is going to be true only when x of m minus 1 is a 0, y of m minus 1 is a 1, and d of m minus 1 is also a 1? No other row of this entire table can possibly make the conjunction here, the expression, to be a 1. Does that make sense? Yep. I'm not sure what you mean by equivalent to what. No, we are looking at the 0, 1, 1. So when x minus 1, x of m minus 1 is 0, the negation is going to be a 1. When y of m minus 1 is 1, what? We are not dealing with it yet. We're only dealing with the fourth row from the top. We'll work on it. But are we convinced that this expression here is a 1 only for the fourth row? Okay, we're good with that. So now we work on another expression that will only be true on the fifth row. So we take x of m minus 1 as is, and then we negate y m minus 1, put a negation here, and then we also negate d of m minus 1. Are we convinced the second conjunction is true only for the fifth row? No other row would give us a 1 except for the fifth row in the truth table. Are we good? Okay. So now if I put a or here, don't you think this captures the overflow? All right. And that's exactly how overflow is defined. There's no need to take a picture because they're all in the notes. I wrote all of this stuff already. Yes, go ahead. You, I suppose you can use other operators. I'm just using the regular Boolean operators. So in my notation, okay, this is usually expressed as this is a multiplication, so it just kind of goes away. Yeah, there's no actual notation. So in okay, so this is my usual notation because I don't like to use ampersand ampersand and stuff like that. And the and minus one. So what looks like multiplication is conjunction, and what looks like addition is disjunction. That notation was introduced when? Day one of this class. Okay, so you might want to go back and review the notes on the notations. Okay, and what kind of people would use this notation? Because my notes also mentioned what kind of people would use which notation? Computer engineers. Yep. Yes, go ahead. Yep. 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 That's a general idea. You can, but the as a Boolean expression. Oh, I forgot about this exclamation point here. You can do it that way, if and only if. Yep. So you're basically looking at x and say, is x different from both y and d? That's basically what you're asking. Yep. But in order to make this easy to understand, I'm just using the logical operators that we are all familiar with. All right. So are we good with this overflow definition? Okay. So now we look at this. Okay, we look at the sign bit. The sign bit is really just d of m minus one. It is the sign bit of the difference. By definition, this is how s as a flag is designated. So now we look at s, and then we look at overflow, and then we ask is x actually less than y? Okay, this is a bad way to put it. Okay, let me be more thorough. And this is basically v s xm is less than v s ym. This is the reason why I introduced the whole concept of vs. Because if I just say x is less than y, then the question is, it's confusing. Are we looking at a signed interpretation or the unsigned interpretation? There's no confusion here. Does that make sense? And that's the reason why I introduce these definitions is so when I need to talk about these things, there's no confusion whatsoever. I'm looking at the signed interpretation of the bit patterns. Okay, two independent variables, four rows in the truth table. Okay, so when the overflow is a zero, it means the difference is correct. If the difference is correct, then the sign bit of the difference will tell us exactly whether x is less than y or not. So that means on the rows where overflow is a zero, this one means, okay, what do I put over here? Is the signed value of x less than the signed value of y for the first row? Okay, let me repeat the question. Overflow says the difference is correctly represented in D, and the sign bit, which is the most significant bit of the difference, is a zero, which means it's not negative. So x minus y is not negative. So it's no. Okay, so that's a zero over here. And now we move on to the third row because overflow is still a zero. So that means the difference is correct. The difference is negative, which means x minus 1 is negative. What do we know about the sign representation of the sign interpretation of x is less than the sign interpretation of y? It is true. Very good. Now we go to the second row, this one here. We have an overflow. When we have an overflow, the difference is not correctly represented, which means the zero is not right. So what should I put here as a conclusion? Is VSX less than VSY or not? It is true. Very good. What about the last row? False. Okay, very good. Another exclusive OR. Very good. All right. So that means if I want to define an L flag, okay, then the L flag, if I want to define an L flag where L is 1, if and only if VSXM is less than VSYM, that's how I want to define L, then based on these observations, then it can simply be defined as the sign flag of exclusive OR with the overflow flag. Is that okay? So now I have a reliable way to tell whether X is less than Y. If it is unsigned interpretation, easy peasy. I look at T of M, okay? In other words, the most significant T bit will tell me if it is a 1, that means X is less than Y. If not, X is not less than Y. Easy peasy. Unsigned is easy. Signed is a little bit more complicated. You look at the most significant bit of the difference, you exclusive or that with overflow. Overflow itself is computed using a, well, kind of tedious, long Boolean expression, but nonetheless, it is just a Boolean expression. Yes, very good question. I can I can answer that question. We are actually ahead of time, so we are good. So let me run Logisim, and I'll show you something that you will see anyway. I'm just moving up the schedule a little bit. Logisim, there we go. All right. Mm, I was just showing this to not a student of ours, but this is the ALU. And by the way, this is our processor. This is what we'll be programming for the second half of the semester. All right, so we look at this circuit here, and then we look at the overflow flag. All right, so I'm just going to highlight the part of the circuit that would do the overflow calculation based on what we have talked about today. This portion. Okay, so with this portion here, I'm just going to point to the screen here. S1 is the sign bit of X, S2 is the sign bit of Y, S out is the sign bit of the difference. So you have two AND gates here. This one is negated, these two are negated. So we are still looking at the negation of X and Y and D with the first AND gate. The second AND gate is looking at X not negated, Y negated, and D also negated. And then these two output, the result of the two AND gates are ORed, just like in the equation. So this circuit here is the equivalent circuit to perform that computation that we talked about earlier. So this is all inside what we call the ALU, which is the arithmetic and logic unit of the processor that we'll be using for this class. And the flag that it is sending out is stored somewhere, okay, so that we can actually use it later on for decision-making process, purposes. But it's too early to look at the rest of the circuit. But since somebody asked about the circuit representation of the equation, it's just this part here. That's the circuit. It is well, it's only for signed. It unsigned has no sign bit, or the sign bit has no significance in an unsigned interpretation. Right. So are we doing okay so far? Okay. All right. Excellent. Let's see where are we? There we go. All right. So there are a lot of proofs here, but and as I said, you only have to pay attention to the green rectangles, and let's read the green rectangles here. Overflow is x subscript m minus 1 and the negation of y subscript m minus 1 and the negation of y d subscript m minus 1, or okay, the negation of x subscript m minus 1 and y subscript m minus 1 and d subscript m minus 1 is all here. Okay, so everything that we talked about today in the lecture in the tablet is already here in the notes. Um, and it even says the overflow flag is the one if and only if vsx minus xm minus vsym is out of range, which is also the whole point that I was trying to make in the half an hour or so. And then the S flag being defined as the most significant bit of the difference is here. And then the L flag being the exclusive or between the sign flag and the overflow flag is here. And L equals to 1 if and only if VSXM is less than VSYM. They sound like the names of Elon Musk's children. So when he has twins, like one is a boy and one is a girl, then there will be VSXM and VSYM. And then when he has a second batch, another twins, it'll be VUXM and VUYM. I have already chosen the names for Elon Musk's future offsprings, which I guarantee will happen from his track record. Hmm? R2D2 is way too common for him. Or he might use Greek letters. beta is not that cool anymore. Beta is just beta. But are we doing okay so far with this material? Okay, so everything that is outside of the green boxes are rationale. Okay, how do we know this works? Okay, so there are three questions. Okay, that I think everybody should ask in every class, especially in a STEM class: what, how, and why. Okay, so the what is in the green boxes. Okay, how that works is outside of the green boxes. Why is a little bit difficult because all of these are used later on. So what you need to know right now is, how are we going to use these things? Well, okay, think about C programming or C++ programming to you guys. What is the most basic Boolean expression that gives you either an answer of true or false that you can use to, in a if then else statement or in a loop to decide when to get out of a loop? What is the simplest kind of expression that you use? It's usually a comparison of some kind, right? So that's exactly what we are talking about here. This forms the most basic mechanism for a processor to make decisions. Is it less than or not? And you would think that doesn't amount to much. Well, that's exactly how the processor works. Okay, a lot of things that are complicated, they're all performed at the lowest level by simply very simple operations. So right now, we have the three most important mechanism in order to implement everything else. We know how to add, we know how to subtract, and we know how to compare. Okay, with those three, we now have everything that we need inside the ALU, the arithmetic and logic unit. So everything else is kind of like, oh, okay, but we need a lot of support stuff in order to make use of addition, because what are we adding? Where are we storing the result? Okay, so we need that. And we also need a mechanism of going like, how do we let the processor know what is the next thing that we need to do? So that's also something that we need to talk about. But what we are focusing on today is for decision making. Okay, is it or is it not? Is it true or false that something is less than something else? As simple as that. Okay, it forms the foundation of how the computer, how the processor makes decisions. Okay, and I still have 2 more minutes, so this is important. I tweaked today's quiz a little bit. You can only take it using certain network addresses. So if you're using one of the computers in the computer lab, you're fine, not a problem. If your computer or cell phone or tablet, whatever you want to use, is on the LRCCD network, you're fine. Okay. So does anyone think that you might have a problem with the network address restrictions? Because you insist to burn your data plan. I just want to see what happens. Okay, so is there an issue with anyone here who are currently physically present in the class that this will be a problem because you insist I want to burn my data plan just to do the homework assignment for this class? All right, okay, we'll see what happens then. Are you going to be okay, Daniel? Okay. Huh? Oh, right, right, right. Okay, give me a second. Give me a second. So your lab is subtraction and compare. The flags. FLAGS flags. Flags. Yep. All lowercase. Give me a second. Let me turn off the recorder first.